It's a pleasure today to have Boris Altshuler from our neighbor upstate. I've known Boris for a long time. Boris got his degree, his undergraduate degree from Leningrad now, St. Petersburg State University, then went to the Leningrad Institute for Nuclear Physics where he got his PhD in 1979. The amazing thing is in 1980 already, he wrote a paper with Aronoff and Lee, which is sort of the first real advance on Anderson localization, including electron-electron interactions. Anderson got the Nobel Prize for localization. He always wanted to treat the many body problem. I think we're going to hear about that today. But he didn't. He treated the single particle problem, the single electron problem first. And Boris is one of the main contributors to work since then, for the past 37 years, I guess, to fundamental research on the many body problem within disordered systems. After his degree at the Leningrad Institute for Nuclear Physics, he stayed on there for about 10 years. He then went to MIT. At some point in the 90s, he moved down to NEC, across the street from Princeton in Princeton, New Jersey. He worked a long time to try and get him to come to Princeton, which he did eventually. Stayed for about 10 years before he moved upstate here to Columbia. So he's won several awards: the Hewlett-Packard Physics Prize, Buckley Prize, a member of the National Academy, the American Academy, and he's going to tell us today about Anderson localization looking forward. Boris?
Thank you. So I had some difficulty preparing to this talk because I was here some time ago. Actually, it was exactly 6 years from now. It was December 1st, 2011. And at that time, I also already was speaking about many body localization obviously, I don't want to repeat myself, but at the same time, the story which I'm going to tell you is very strongly connected with this phenomenon of many body localization, and that's why I will have to apologize for those who have been in 6 years ago on my colloquium and will have to listen it again. So what I would like to discuss is kind of some problem that appears equally in classical and quantum systems, and this is the problem of ergodicity. And what I just want to tell is that we clearly in quantum physics have a lot of help from classical physics, all things like semi-classics, WKB, and so on. But once in a while, there is some quantum problem which eliminates also certain things in classical physics. And a good example is this heat theorem, and you cannot prove or disprove the Nernst theorem without quantum mechanics, and there was actually pretty interesting discussion between Nernst and Einstein about this heat theorem and about the possibility to reach zero temperature. And Einstein was pretty harsh. You can see how he criticized Nernst. But what I think they did not discuss, and which is quite important, is that it's not only difficult to reach zero temperature. It's sometimes impossible to reach thermal equilibrium being pretty close to ground state. And the state which is not reaching the thermal equilibrium will be, I will call them non-ergodic, and we'll discuss how they are developed and what are their properties in both classical and quantum cases. What I will speak about will be some systems with large number of degrees of freedom, not maybe infinite, but very large, and completely isolated from outside world. I don't want to speak about thermostat. I just want to understand whether it's left alone will get to thermal equilibrium or not. And there are some systems that are supposed to be very weakly connected with outside world. You can name quantum gases or systems which our colleagues try to assemble in order to perform quantum computation, where deliberately all kind of decoherence from the environment are being suppressed. And in principle, you can speak about universe, but I'm not a big fan of these philosophical discussions. So we will speak about dynamical systems. And for these dynamical systems, there are two limits. One limit is known as integrable system, where you can separate variables and reduce this problem, which is d-dimensional, into d one-dimensional problems, which you can solve using these angle action variables, and you will end up with d integrals of motion. Another limit is what is called chaos, and in this case, no integrals of motion, no conserved quantities, and the only one is actually total energy. And in the first case, we have this conserved quantity, and if you will think about energy shell, which has dimension 2d minus 1, because phase space has dimension 2d, and energy shell is one dimension less. And at the same time, for integrable system, all the trajectories are concentrated on something called invariant tori, which has dimension d. And for d bigger than 2, this is smaller, and it means that this system is not spreading all over the energy shell. In contrast with these systems that we are thinking about when we are discussing statistical mechanics, and this statistical mechanics is based on the equipartition postulate, which tells that all states with the same energy are appearing with the same probability, which means that we should spread everything into over the energy shell. And what I would like to discuss is what happens in between. What happens if you have some underground integrable system, but as it usually happens in life, it's difficult, and there are certain perturbations which, any problems?
Just with the computer.
I don't know what is going on, sorry. What I would like to discuss is how you can evolve from integrable system to this chaotic one if you add certain perturbation which violates integrability. And there is some coupling constant which controls this violation. And then when we are speaking about classical systems, and I will just discuss several examples. At very small, very weak perturbation, there is so-called CAM theorem, which tells that the tori are not destroyed, and that's why there will be no chaos. But interesting things happen far outside this CAM region, and you have a lot of systems which are neither integrable nor even CAM systems, but also not ergodic. And let me just give you some examples. So first example is so-called Fermi pasta Ulam problem. So it's basically a set of anharmonic oscillators. There is cubic anharmonicity and force power anharmonicity, and they are connected. And it was basically the first problem which was analyzed by a supercomputer at that time. It was in Los Alamos, and they just built this Maniac machine, which was real supercomputer at that time, and they made started to simulate this this system of connected anharmonic oscillators in the following way, that they excite just a small number of them and try to see how this energy will be distributed over the modes. And some people call it start of experimental mathematics, but it's, you know, depends on enthusiasm. So the conclusion was actually slightly disappointing, and as Ulam recollects, it was surprising for Fermi because they found actually no mixing of the of different modes, no thermalization, and the longer they would go, the more non-ergodic behavior was, and it lasts and lasts. There was a few years ago a conference called 50 Years of the Fermi pasta Ulam Problem, where people using computers of our time observe more or less the same behavior. So we have clearly a system which is not integrable at all, and at the same time there is no intention to get ergodic. Another example I like very much, it is nothing but our solar system. And of course, Newton was the person who really understood what happens when a planet goes around the sun, and what was, you know, what he liked very much was that there is a periodic motion with certain orbit, and everything is nice and ordered. So he described behavior of the planets, but he was too smart to stop here, because he understood that planets also interact with each other. And in spite of the fact that all planets make only, you know, correction to the mass of the solar system in the third digit, nevertheless, there will be some interaction, and there should be some irregularities in the motion of the planets, and for Newton it was not acceptable, because things should be perfect, and he found nothing better than to decide that God once in a while intervenes, makes what he called reformation, and puts everything back into this motion. And Leibniz, who was big opponent of Newton, criticized him for reducing God for simple miracle. So this was the level of understanding of this problem at the time. Now, what do we know now about it? Actually, people, there is a community of really smart people, and they have state-of-the-art computers, and they actually can predict reliably what will happen with solar system in future, and tell you what is particular position of each planet, let's say in 100 years and in 1,000 years and in million years. But they can tell you nothing reliable for time bigger than several tenths of the million of years. And it's still much smaller than life of the solar system, which I hope I will not make you too sad by telling that we have only 8 billion years left before sun will explode. But all this, at all this time, it's impossible to predict because we simply don't know the original conditions. I mean, if somebody will now get out or get in, it can influence position of Jupiter in a couple of billion years by, you know, phase equal to almost pi. So there is chaos. And then people discuss it in terms of probabilities, and I read somewhere that there is 1% of probability that before sun explodes, Mercury will collide with Venus, and there is also some probability of collision between Earth and Mars and things like that. But it is about probabilities, and clearly there is no even signature of thermalization. In spite of the fact that the motion is clearly not motion of integrable system. And I have to repeat that by any estimations we are very far from the region where Kamm theorem can tell us anything. I forgot, planets should be less than 1 gram in order for Kamm theorem to be useful. And the third example is something that we meet all the time. It's glass. So again, we have set of atoms which, let's say, were quenched from the liquid phase and form this state, which is clearly not thermal state because the energy is very far from the ground state, which is energy of the crystal. And again, we know that glasses live longer. For example, people would find vases made in Egyptian like 10 years ago, and still they are in glassy state, not crystalline. But the most impressive is glass on the moon, which was there at least 1 billion of years, and again, there is no crystallization. So although there is still, again, some scholastic discussion whether glassy state is true state of matter or it is just extremely liquid with extremely high viscosity, and at very long times it will crystallize. But these times are clearly much bigger than lifetime of universe, and again, this is different state of matter. So this is classical systems. Now what about quantum systems? And solar system has a good quantum analog, which is basically multi-electron atom. So in solar system also, if you neglect interaction between the planets, the angular momenta and energy of each of the planets will be conserved. But it's not conserved exactly as we understand it. It changes only very quickly and very slowly. But in atoms, we believe that it doesn't change at all. And this is in spite of the fact that interaction between electrons is actually much stronger, because the gravity is proportional to the masses, and charge of the electrons is not so much smaller than charge of the nuclei. So this phenomena which makes the quantum system much more stable is basically analog of the localization. And this is one of the simple examples of many body localization, when you create electrons on certain orbitals, and although the wave function of this excited state is not exactly what it would be without interaction between electrons, but it is not too far from that. So it looks in a following way. If you, in quantum mechanics, you have possibility to construct linear combinations of different states. This is called fancy word entanglement. And if you take into account that all these integrals of motion in quantum mechanics are quantized, what you can do, you can consider states which correspond to particular set of the quantum numbers of non-perturbed system without interaction between electrons. And then what you can do, you can expand it expand the eigenstate in series of these Fock states, and then you have at least two different possibilities. Either state will be localized, which will mean that it is only finite number of terms in this sum which is important, or it will be extended, and there will be macroscopically many terms that we need to take into account in order to describe a particular state of our system. So the way of discussing the quantum problem in general, I mean quantum problem of this type, where we have integrable part and perturbation, what we can do, we can think in terms of the space of these integrals of motion, let's say set of angular momenta and energies of the planet, and then if system is integrable, then its state is just a point in this space which does not move with time, and it corresponds to this invariant tori that appears in mechanics. And there is no much difference from the quantum system, except that there is quantization, and this space is not continuous anymore. It's more like a lattice. Just to give you an example, if you have a rectangular billiard, then your momenta, both horizontal and vertical components, are quantized and form this lattice. And you can introduce the energy shell here, and then you can start violating this integrability. Here you obviously can separate variables, and when you do it for classical system. If you are, say, in the calm regime, the point will not go too far from the original point. So there will be some motion of this set of integrals of motion, but it will be very restricted. And this is this corresponds to in quantum mechanics to eigenfunction being a linear combination of states taken from small region of the energy shell or near the energy shell, rather than states in all energy shell being taken with the same weights. So basically, this many body localization is extension of the usual Anderson localization of a quantum particle in finite dimensional space to the Hilbert space. So we have a wave function of whole system which is localized in Hilbert space rather than localization of single quantum particle in d-dimensional space. And if for ordinary Anderson localization you just have absence of diffusion and wave packet is not spreading, here, for example, you can show that if you have interacting particles and they are decoupled from the outside world, then in the presence of disorder you will have a region in temperatures where particle simply cannot move because many body wave function is localized. And at the same time, if you increase temperature, which means increase the energy of the state, you can undergo transition into extended states where there is some kind of final conductivity, again, without any foreign assistance. And there is one more thing that I want to add to this story, which is that this analogy between classical calm behavior and the quantum localization actually is correct only for systems with 2 degrees of freedom, and the reason is so-called Arnold diffusion. Because if you have the 2 degrees of freedom, then the dimension of the tori is 2, and the dimension of the energy shell is 3. And if you embed 2-dimensional manifold into 3-dimensional space, then this manifold always has inside and outside. And because of that, because Ham tells us that tori exist, but classical trajectories cannot cross each other, you cannot get from inside of each tori to outside. However, if number of dimensions is bigger than 2, then difference in dimension between energy shell and the tori is bigger than 1. And we have situation like, for example, a circle in 3-dimensional space. And circle in 3-dimensional space doesn't have inside and outside. And even if you have very densely located circles, you still can find a way around them somehow. And what it tells that us that the picture with in large number of dimensions is not as simple. The trajectory will not be always finite. Once in a while it will go somewhere. And there is so-called Arnold diffusion when you go and spread over the energy shell, but it goes very slowly because this motion is not it's not very easy because there are all these come to right. So the point is that when you have a large number of dimensions, then there is no really calm behavior. This tori will get destroyed, and there is no full localization. Okay, but the point that I want to make is that you don't even need the existence of tori. What happens in the system which is not integrable but not far from integrable is that there is a whole lot of stable orbits, and if the system finds itself close to one of the stable orbits, it goes for a long time along this orbit, then maybe leaves it, meets another closed orbit, and again goes for a long time. And it means that it will be maybe spreaded, but not uniformly at all. It will be always in the vicinity of the periodic orbit. For example, state of our solar system is, of course, not a tori, but rather a very stable periodic orbit in this 9 times 3 plus dimensional space. And this is actually, there is all joke that when a physicist is asked to evaluate stability of a table with 4 legs, then first step is to evaluate stability of a table with 1 leg, then evaluate stability with infinite number of legs, and then spend the whole rest of the life trying to solve the problem with arbitrary number of legs. And I think what mathematicians are different from us. I don't want to tell anything bad about mathematicians. They are very smart. And for this, there is a reason, but they never go to step number 2. You cannot really ask a mathematician what would be the behavior of a system with infinite number of degrees of freedom, or what we call the thermodynamic limit. They are happy with understanding 2-dimensional, 2 degrees of freedom. They have some story of Arnold diffusion, 3 degrees of freedom, but I have not heard about discussion of large degrees of freedom on the mathematical level. But let me just show it in the same picture. So it is nothing really concrete here. I just want to illustrate the idea that if you have quantum problem, you have many body localization. So at low enough temperature, conductivity is exactly 0. While in classical problem, you don't have localization. So conductivity would be always finite, but maybe very small. What quantum mechanics does, it basically localizes this Arnold diffusion. But the whole region which we call bad metal is more or less the same in the classical and the quantum case. And this is what I would like to discuss. What is the behavior where we have this bad metal, and one particle picture which we usually apply, like Drude formula, is badly wrong. And this also shows the big difference between the conventional Anderson localization and many body localization. Because for one particle case, it is basically not quantum problem. It's problem of wave dynamics. People observed Anderson localization of sound and microwave and whatever, which has nothing to do with quantum mechanics. But this many body localization is truly quantum phenomena. It simply does not exist in classical case. The question now is the following, that we know that localized regime is not ergodic, simply because you don't spread at all over the energy shell. But the question is, if you undergo the transition to extended states, are you getting into the ergodic state or not? And this is actually a pretty tricky problem, and there are certain discussions. And what I would like to do is to give you some arguments in favor of this non-ergodic behavior. The point is that when we think about ordinary Anderson localization in final dimensional space, then wave function becomes ergodic. I will give you better definition in a short while, as soon as we undergo the transition. So there are non-ergodic states, but just in the transition point. As soon as you move outside, the states become ergodic. But still, what happens in many body case? And let me just give a little bit more of definition. So suppose you have this Anderson model, which is basically a tight binding model, H0, and where, in contrast with this textbook tight binding model, on-site energies are random in certain interval between minus W and W. And what are the wave function? You can characterize them in the following way. Suppose we have size of the system which tends to infinity. And what we can do, we can calculate so-called moments of inverse participation ratio, which is sum over all sides of wave function to the power 2q. And of course, this for q equal 1, it is basically normalization condition, so it's always 1. And in general, you can tell that these moments of the inverse participation ratio scale as some power of the system size, some negative power of the system size. And it is equal to 0 for q equal 1. Now, if everything is ergodic, then you can tell that more or less each term in this sum is actually the same, equal to 1 over n in certain power. And if you will calculate this inverse participation ratio under this condition, you will find that the exponent is equal to q minus 1. Now, it is possible to tell, actually this is possible to prove, that if you will calculate the fluctuation of this moment of inverse participation ratio from one realization of disorder to another, then in the ergodic case, it tends to 0 when system size goes to 0. And if it is different from this ergodic value, then this squared difference is remains finite when system size goes to infinity. So this is clear difference between the averaging over the realizations and averaging over the space. I just want to remind that originally in the definition of Boltzmann, it is ergodicity is equivalence of average over space and over time. And here in quantum mechanics, you can have good definition. It's basically spatial average and ensemble average. So this is more or less the picture that I want to claim that you can have first Anderson transition from insulator to extended but not ergodic system, and then there will be either crossover or transition from non-ergodic to ergodic, which is completely different type of phase transition. So if we have states that are localized, then of course this exponent tau is equal to 0, because all terms are finite and there is finite number of those. And in general, you can introduce these so-called fractal dimensions that are a ratio of this tau divided by its ergodic value. And this d, that is anomalous fractal dimension, if all it depends on q and differs from 1, the situation is called multifractal, just for definition. So the question is what kind of states we have after the delocalization, whether they immediately get the all dq equal to 1, or there can be dq different from 1. And it would mean that wave function, although it extended, will occupy still measure 0 of the total allowed number of states. So as I told in the finite dimensional localization, you have this non-ergodic states, but only in the critical regime. And what I want to tell that this story of many body localization, for example, of interacting quantum particles with some localized one-particle states, it is actually not far from just one particle problem, but not in this finite dimensional space, but rather in the on so-called Bethe lattice. And Bethe lattice is this strange object where we have some generations, and each side of a certain generation is connected with k sides in the next generation. So it means that number of the sides involved increases exponentially with number of generations. And the question is why this one particle Anderson model on the Bethe lattice is relevant. And the answer is the following. This is actually the most important difference between conventional and many body localizations. So if you will calculate the number of sites in finite dimensional space at a certain distance from a particular site, it increases as a power of the distance. While the matrix element of the tunneling is increasing exponentially with the distance. Which means that if we're looking for two sites that are in resonance, which means that matrix element is of the order of order bigger than the difference in the on-site energies, then these resonances will be predominantly close to our particular case. And for Bethe lattice, it means the number of sites at given distance increases exponentially, and matrix element decreases exponentially. So we have competition between two exponents, which gives us transition, but also it means that these resonances to a particular state can be typically arbitrary far separated in space, because although the matrix element increases exponentially, there are so many states that it is more probable to find a resonance between them. And this is just to demonstrate it as a cartoon. So in finite dimensional case, wave function is actually, when you approach the transition, just increases localization length. It becomes fatter and fatter, but still remains predominantly one peak or several peaks, but located close to each other. While when you take many body localization, you are creating a state with relatively narrow peaks, but the number of peaks is increasing and becomes exponential at the transition point. And that's why I don't like very much when people speak about kind of approximate conservation laws and approximate quantum numbers in the many body localized state, because what you will have entanglement of states with very maybe very different set of quantum numbers. And what I want to tell is that there is, why I have this again, somehow. Yeah, okay. So then what I would like to discuss is basically behavior of the wave functions on this Bethe lattice. And the cleanest case is so-called Cayley tree, when you just have central state and then there are states in first generation, second, and so on, and you get infinitely many generations. But the problem with this Cayley tree is that you always have a good fraction, sometimes most of the sites which are on the boundary, and that's why it is not very representative of the bulk behavior. So what we studied numerically was so-called random regular graph. It's actually a pretty interesting set of systems where you have n sites and you have an ensemble of graphs that you get by connecting each site somehow with k plus 1 other sites. And what is known as locally, this thing behaves as a Bethe lattice. And what you can do numerically, you can just take pretty big random regular graphs. You have a lot of them with large n. It increases very quickly, the number. And the study the spectrum of the Anderson model. And
Boy, but you insist that every site has k connections, the same number of connections.
Yeah, no, I not insist. It is a model. It is a model.
But in the model, it's not on average, but every side?
Yes, yes. Of course you can then modify model and make it random, but what we know, the experience in ordinary localization is that qualitatively nothing changes when you change the model of disorder. It can be delta correlated, not delta correlated, Gaussian, non-Gaussian. Things are, the statements are pretty robust. So I think the main and dominating property is the fact that you have exponentially large number of states. What I think I have to do is, I have time probably in a few minutes just to give you some insight of what you can do analytically or semi-analytically. And this is set of my collaborators, mostly Lev Yoffe, Vladimir Kravtsov, and Emilia Cuevas. What you can do, you can, as I told, either just calculate the wave functions, just evaluate them and calculate these anomalous fractal dimensions, or you can follow the path more or less described by Anderson. And what he did, and what many people started with afterwards, is to discuss not just global density of states, but local density of states. When you calculate the sum over all states that have close energy close to certain energy, and at the same time you weight it with the wave function so that states, if there is localization, you will take into account only localized states, and if it is ergodic, it will not be very different from global density of states. And of course, in order to get something reasonable, you have to regularize it. And usual way of regularization, this delta function, is to make it Lorentzian with certain widths eta. And then what you can do, you can plot the dependence of the distribution function of this local density of states as a function of the rho at different etas. And at finite but small eta, it is usually something that has a peak at certain rho, which is very different from the average density of states. If you are deep in the metal, this peak is actually close to the average value, and mean and typical values of local density of states are close to each other. But in the non-ergodic state, what you have this peak which is very asymmetric. And what you can do, you can analyze this distribution function, and there is there is a way of doing it analytically using so-called replica method and breaking replica symmetry, and just not to give you too much of the information, this is what we got when we started to calculate this anomalous dimension of the this fractal dimension, I think here it is what you would call D1. And basically it corresponds to so-called Shannon entropy in probability theory. And there are different things here, and the solid line is basically our analytical solution, and this vertical lines is certain numerics which is called population dynamics, and the circuits is a result of just exact diagonalization. And what you can see that it is pretty good agreement, and in the interval between something about somewhere between 17 and 18, the transition happens. This is the old story. There was this paper of Altshuler, Anderson, and Towles, who were studying the localization on the Bethe lattice. And then this fractal dimension actually changes from 0 to 1, and it reaches 1 somewhere at W4.6. So there is a big interval of the parameters where it is clearly this fractal dimension is different from both 1 and 0, and this interval would be non-ergodic. And I probably will not discuss the way of getting this phase diagram. There is no difference between red and orange, but you see that in the plane of disorder versus energy, you have a region of localized states and region of ergodic and extended states, and in between there is a region of non-ergodic and extended, and when you increase this k, this region more or less covers all the available space in this plane. And just to give you unfortunately, I have no time. It's quite involved and interesting theoretical story. I just want to show that what happens if you do this approach consistently. This is the value of critical disorder W at which the Anderson transition happens. And there was this formula of Altshuler, Towles, and Anderson, and there were pretty involved calculations of Giulio Biroli. And as you can see, the discrepancy between second and third lines is pretty big, and it increases when you increase the connectivity of this Bethe lattice or random regular graph. And the formula which we obtained by breaking replical symmetry breaking and taking into account symmetry of the problem, there is some hidden symmetry. You can see that there is pretty good agreement with numerical calculation to the extent that I don't know which result is closer to the truly correct one. So it just demonstrates that this approach is relevant, and that this analytical solution for the fractal dimension it is actually Correct. So I will not bother you with more technical details. What I think is clear is that there are pretty good, pretty strong arguments in favor of existence of this non-ergodic quantum states. And again, I don't have time to elaborate on that, but existence of these states might be pretty important for whole field of quantum computation, because if you, just to tell you, if you want to store some quantum information, you don't want to use localized states because it would be very difficult to find it. And you don't want to do ergodic states because they can carry no information. So basically, the most reliable is these non-ergodic states, and hopefully at least some way of using these quantum computers will be in the regime where wave functions of this quantum computer is in the non-ergodic state. But to return to this question that I addressed in the very beginning, when you think about classical problems, you basically, it's completely fragmented. Every particular problem has its own community. People are doing some calculation and make some discussions, but there is no real generic approach. I think in quantum mechanics there is one, and maybe it will help to understand something more general in this nonlinear physics and all these problems of problems similar to Fermi past Ulam. So I think I've finished. Thank you very much for your attention.
It's a very interesting state, this non-ergodic sort of localized state, but I don't understand how you imagine to go from this to pure ergodic state, or you claim that there is no such thing as truly ergodic state.
No, I mean, in this approximation, which is one-step replica symmetry breaking, which we can discuss how reliable it is. In this approximation, there is true transition, because there are
transition from non-ergodic state.
Yeah, from non-ergodic to ergodic, because when you go out of the transition, this parameter, which is size of the group in which you break all your replicas, equation for it has two solutions. And there is clear region when you have to take into account a solution that is smaller than one, but at certain point, the solution you have to take is m equal to 1. So it happens at one point. But it is, of course, not a strong argument in favor of transition. It easily can be crossover if you, will come up with approximation that then is better. So I think this is still open question, and I would love to understand the answer, because it's completely different type of phase transitions. However, from the
control parameter is your lambda.
Control parameter here is disorder. So once more, you have this random regular graph.
K?
No, W. You can see you can change W at given K or vice versa, because everything is moving. But I think it's better to speak about W. Again, all approaches have certain deficiencies. Exact diagonalization, you can go too far. just to give you an example, what you can do is maybe 10 to the 5 sides. And if you have a system of spins 1/2, and spins is 2 to the n states. So if you have just 20, 30 qubits, it's already much bigger. You can do population dynamics, which is you can go to much bigger system, but it's unclear how it's connected. And again, analytical approach is also based on something which some people love and some people hate, which is this replicate symmetry breaking approach. So everything has this or that, but the fact that they give more or less the same behavior suggests that we are not too far from that. And hopefully there would be better. It actually a lot of interesting twists for a theorist here.
I just missed it. So on the diagram, when you have little lambda, if you go away from the CAM regime, you are necessarily in the strongly coupled regime when you are non-ergodic, or there is some interval in which you can be
you see, I think that generic behavior is that, first of all, at large d, size of CAM region is negligible, because, I mean, tori gets broken when there is among all the frequencies, and each tori is characterized by d frequencies. And when two of them become commensurate, you break it. And if you have very many frequencies, probability of that is pretty high. So they get broken pretty quickly. And then you get in a situation when there is no toris anymore, but there are still a lot of stable orbits. And I think this state is a good candidate for becoming non-ergodic. And I think examples that we have are more or less like that. And yeah, and what
so they're not necessarily strong.
yeah, yeah. So, for example, what you would do for Fermi pasta Ulam, you will just start with harmonic oscillator and start to change on harmonicity and try to see whether it goes to ergodic state or not. As far as I understand, it does not even for very strong harmonicity. But this is another story. I'm not a big expert in that particular model, but
just to be clear, did you say that it is or is not known whether it's a real whether it's a transition or a crossover?
Yes, I don't think that there is clear answer because every transition for finite size system looks like crossover. As you know, it's difficult to distinguish. Nobody really knows how to describe this transport on beta lattice in the limit of weak disorder. It's actually opposite to what we got used to finite dimension. That weak disorder looks like just do perturbation theory. It doesn't work for these systems. I think if and when we will learn how to deal with weak disorder, we could be a little bit more reliable. Even critical behavior of Anderson transition on the beta lattice is not as clear, and there were several, discussions based on nonlinear sigma model that singularity is not power-like but exponential or square root in the exponent, and even this is still is not completely finished. But this transition is still much closer to what we got used to than this ergodic non-ergodic. So the answer is I don't know, and I don't know what would be the real physical, observable that will feel this difference. Thank you.